Okay, so we're at the point where we have now upgraded our algebra to the Dixon algebra, RCHO, which is a 32 complex dimensional algebra. And we would like to eventually calculate standard model scattering amplitudes. So our first step is to try to model the full particle content of the standard model, much in the way that we modeled Lorentz scalars, spinors, 4 vectors in the field string tensor using the complex quaternions. Okay, well, what's the standard model's full particle content? As you know, the standard model's gauge group is SU3 cross SU2 cross U1 over Z6. And under this gauge group, the standard model has this very long and seemingly arbitrary list of irreducible representations. So the first entry here in brackets refers to the irrep under SU3 color. The second refers to the irrep under SU2 left. And the third refers to weak hypercharge. And the subscript at the end refers to the multiplicity of these unconstrained off-shell states. Now, if we add up all of the degrees of freedom in this list, taking every particle as unconstrained, counting the Higgs as its own independent space, and finally including an additional set of 3 sterile neutrinos, we then have 244 degrees of freedom in total. So roughly 250. That's quite a lot. Okay, so let's check back on our RCHO algebra. How big was it? Well, RCHO is just 64 real dimensional. So it seems like we might be stuck. How are we going to model roughly 250 real off-shell unconstrained degrees of freedom of the standard model when all we have to work with is a 64 real dimensional algebra? Well, one idea is to take a hint from nature. Nature succeeds in describing the entire human genome using just 4 bases, A, C, T, and G. Well, how does it do this? Nature accomplishes this not by considering those 4 bases alone, but instead by considering sequences of the bases. So let's see what would happen if we were to consider sequences of RCHO elements, one being multiplied onto another. Might we be able to describe the fermions and bosons of the standard model inside these sequences? Now, sequentially multiplying RCHO elements onto RCHO elements generates something familiar to mathematicians known as its multiplication algebra. And you can think of RCHO's full multiplication algebra as being isomorphic as a matrix algebra to the 32 by 32 complex matrices, or to the complex Clifford algebra CL10. Now it's generated using 10 objects, which we're going to call gamma J. And you can think of these 10 gamma J's as being like the 4 A, C, T, and G bases of genetic sequences. These 10 gammas are going to generate the complex Clifford algebra CL10. Now this is CL10, but it's CL10 with a lot of extra structure due to the fact that it's being generated by RCHO. Now, this extra structure is going to give us a number of natural ways that we can break CL10 up. Now, it turns out that we can write RCHO's full multiplication algebra as a factorization that's interesting on mathematical grounds. That is, we can split it up. We can split up complex CL10 as the real CL08, familiar from the Bott periodicity of real Clifford algebras, and complex CL2, familiar from the Bott periodicity of complex Clifford algebras. This might relate to what John Baez and others call the Tenfold Way. As a physical interpretation, I would like to identify the standard model's unconstrained states with CL08. And then there's going to be this extra complex CL2 factor left over. Now, given the isomorphism between complex CL2 and the real CL30, we may be able to adopt an interpretation that the CL30 part represents the rudimentary algebraic beginnings of a 3-dimensional space. That is, the 3 legs of an evolving triad. From here, we might try to incorporate gravity. Now, in geometric terms, this setup would give us the algebraic building blocks for an emergent 11-dimensional space. We might find ourselves with a 3-dimensional spatial base manifold and a fiber producing standard model degrees of freedom.